Hi, I'm Paul. We're doing Leetcode must-know interview questions. Today's challenge is binary search tree iterator. Rating, medium. Implement the BST iterator class that represents an iterator over the in-order traversal of a binary search tree. Okay, so there's three kinds of traversals. A binary search tree: in order, pre-order, post-order. In order is left node right. So is there an example here of what a tree looks like? Okay, yeah, so if we were going to do an in-order traversal of this tree, here is the root. We don't start at the root. We process the left subtree and then the root and then the right subtree. And actually, well, I'll leave that for later. There's a constructor, BST iterator, and it takes as input the root of a binary search tree. Initializes an object of the BST iterator class. The root is given as part of the constructor. The pointer should be initialized to a non-existent number smaller than any element in the BST. I don't really know what that means. Boolean has next returns true if there exists a number in the traversal to the right of the pointer, otherwise returns false. Again, I don't understand that either. The right of the pointer. I don't understand the pointer reference at all. Int next moves the pointer to the right, then returns the number at the pointer. They seem to be assuming a certain implementation, which is I don't even know what the implementation would be, but it's not what we're going to do. So anyway, yeah, let's move on for now. Note that by initializing the pointer to a non-existent smallest number, the first call to next will return the smallest element in the BST. Well, yeah, but it seems that baked into this is the assumption that that you're going to get the tree in order. It's an in order traversal. Yeah. That the numbers are not just going to be random numbers in these nodes, that if you did an in-order traversal, like on this example tree, we have the node here, but we start on the left and we get a 3. There's nothing else over there. So we come back to the root. That's a 7. Now we go down here to this node, but we don't process the node because we process, any node, we process it left node right. So we go here to the left. Now we have 9. So far we have 3, 7, 9. Now we're back to this node. That's a 15. And then we go to the right, and that's 20. So, okay. You may assume that next calls will always be valid. There will always be at least a next number when next is called. All right. Constraints: number of nodes is from 1 to 10 to the 5th, 100,000. Is that right? Yeah, 100,000. Values will be from 0 to 100,000. So there's at least one node. We're not going to get a null pointer passed into the constructor. And at most 100,000 calls will be made to hasNext. That's not very many. Could you implement next and hasNext to run in average O1 time? Next, yeah, next is next going to run in O1 time. Yeah, well, I'm not sure that would qualify as O1 time, to be honest with you. And OH memory, H is the height of the tree. The memory shouldn't be a problem. Okay, the tricky thing here is not the in-order traversal, we may have done in-order traversal problems before. I guess the natural way to do it would be recursively. You know, you traverse the right subtree and then the root and then the left subtree. But the twist is that we have an iterator here that requires us to be able to stop in the middle of the traversal and then pick up where we left off. So if we're going to do that, then we need some way to keep track of the nodes that we've processed so far. We need some way to keep track of where we are. And a stack is probably a good way to do that. So let's try this example here, where the first call is to BST iterator. All right, so they're going to pass in the node, the root, which is this 7 node, and we're going to push these nodes. We're going to push 7, and we're going to push everything to the left. We're going to follow left pointers down to a leaf node. And there's only one there, so we're going to push a 3. The reason that we do that is because in-order traversal, again, is... oh, it's going to make me do it again. Thank you. The reason that we do that is that we have to process the nodes to the left of the root first. Okay? So the 3 is on top of the stack. We're going to get to it before we get to the 7. Okay. And that, it's a constructor output. No. Next call is next. So to do a next, we are going to pop the stack. On top of the stack is a 3. And we're going to return the 3. Now, when we pop the stack, we are also going to see if the node that we popped has a right child. Okay? If it does, we're going to add the right child. And we're going to add nodes to the left of the right child. Why are we doing that? Because we have to process those nodes before we get to the root. For example, if 3 had a right child, we got to process that before we process the 7, the root node. The 7 is already on the stack. So if there was a right node here, that would have to be pushed on the stack. In this case, there isn't, so we move to the next call, and that is next. All right, pop the stack, and we get 7. Okay, that's here, 7. Now, when we pop it again, we look to see, is there a right is there a right node? And in this case, there is a right node, and that is 15. So we're going to push it. We're also going to push. We're going to follow left pointers all the way to a leaf on this because those have to be processed before the 15. So we'll follow the left pointer. It goes down to 9. So push the 9. All right. So that takes care of the next. Next call is has next. Well, has next, all has next is going to do is look and see if the stack is empty. And if the stack is not empty, then yes, we have more nodes. So we return true. We'll call next. We will pop the stack and get a 9. Return the 9. 9 doesn't have any child nodes, so we don't have to do anything else. All right, has next. Stack is not empty, so that is true. Next. Next, we are going to pop the stack to 15. Return the 15 and see if 15 has any nodes to the right. And it does. 20 doesn't have any nodes underneath it. So Actually, I should probably underline the fact that we did return the 15. But we're going to have to look for nodes on the right. We have one, it's a 20, and we are going to push it. Okay, has next. Is the stack empty? It's not. So has next is true. Next is going to return the 20, which we pop off the stack. 20 doesn't have any child nodes, so there's nothing else to do. And then the final call here, has next. Well, now the stack is empty, so we return false. All right, so that's the algorithm. Let's see what we can do with an implementation. So we want a class variable here. I'm going to use a stack of tree nodes. Call it stack, and it equals a new stack. I guess I should mention here that stack is considered like kind of a legacy class in Java. Usually we use deques now, D-E-Q-U-E, it's a double-ended Q. You can use it as a queue or a stack, but I don't know. Kind of in the habit of using stacks. It's like, anyway, VST iterator. So we get the root in here, and I'm going to say, I'm going to do one thing here, tree node equals root, because I don't like really messing around with root nodes, modifying root nodes if they're passed into a function. So let's just say while node is not equal to null, while node is not equal to null, stack dot push node, and then the node will go to the left. So in our example, that is where we got the 7 node coming in. We pushed it, and then we pushed the 3 node. All right, private int next. We have to pop the stack. So tree node. You know what? I don't want to call this node because I need that name. Tree node, current node equals stack dot pop. Okay. And then let's say tree node equals current node dot right. Again, when we pop when we do next, we pop a node and then we look to see, does it have any right node, any right does it have a right child? And if it does, we got to put that on the stack. For example, when we popped the 7, we have to look over here and say, well, does it have a right node? It does, the 15. So we got to push the 15, and then we've got to push, 9. We've got to follow left pointers and push the nodes to the left of that. So tree node equals current node right, and then while. I just noticed something here. Well, if you're doing this on a whiteboard, it's not quite as easy to copy and paste things. So probably at this point, it would be good to just go ahead and write the code. While node is not equal to null, stack push node equals node left. And then either mention it at the time, or when somebody says, is there a way you could improve this code? You say, yeah, because I repeated this code here. And it really should be in a method, and then just call the method. If you're doing it on a whiteboard, you're going to have to erase it and write it over again. But for now, we'll do it like this, keeping in mind that it should be in a method. Return. Well, hang on a second. This is actually bothering me. Let's take this out of here, and at the end here we will add a private method. It's not going to return anything. Call it something like push left, and it is going to take a tree node called node. And we'll say while node equals null. Okay, push left, fine. And then up here we will say push left node, and in here we will also say push left node. All right, and then we're going to return a value, an int, which would be current node. That's the node that we popped, dot val. Okay. Has next is just returning whether or not the stack is empty. So we'll return not stack that is empty. All right. I think that is the algorithm that we described. And again, I have to admit, I don't know what I don't know what a lot of this means, like pointers being initialized to non-existent numbers and moving pointers and things like that. I don't know. But I think this is the algorithm that we described, and I think it's valid. I don't know. Let's try it. Accepted. Okay, good. Runtime 2 milliseconds. That's not great, but I don't know. If they're doing 100,000 calls, maybe it's okay. Submit. 17 milliseconds. Yeah, it's so if they're doing a lot of calls, but we still kind of beat the crowd there, I guess. Beat 67.01. All right. So that's it. It's just it's an in-order traversal with a twist, which is you've got to be able to stop in the middle of the in-order traversal and then pick up again where you left off. So you need to keep track of where you're at, and you can do that with a stack. So that is it. What is this called again? That's it for binary search tree iterator. Feel free to like, comment, what else? Subscribe, and see you next time.